Am I audible now?
Yes, sir.
Okay. So, good evening and welcome to the week 4 of the live interaction session of the brief introduction to microsensor. The course instructor of this course is Professor Santanu Talukdar from ISR Bhopal. I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. So, this is our last class for this series of lectures on microsensors. So this is a brief about me, the class link that we used. All these recordings of the classes will be available on my YouTube channel. And in case you need to uh, ask something, write, or like seek collaboration or something, you can contact me over this email. So before going into the case studies that has been discussed in this week, any questions which we have covered till now? You are welcome to ask. Anyone can ask. Yes, any questions? And that crystal structure and all that we will discuss in today's lecture. At the end of today's lecture, we will be discussing that. Yeah, apart from that, any other questions anyone have? Okay, so let's start with some case studies. So we have already uh, seen what are microsensors. We have even seen uh, like what are the processes that are used to fabricate these microsensors or MEMS sensors. Okay, and specifically we have seen like one process in more details, that is lithography. And as I said, that is one of the most like important part where which is used in most of the semiconductor fabrication processes. And if you go to the semiconductor fabrication part, you will see that 70 to 80% cost of fabrication is due to lithography. Like that is a significant cost, as well as it is one of the most precise process we can say that requires a lot of skill. This whole semiconductor fabrication and these things requires a lot of skills apart from theoretical knowledge, right? So in this lecture, we are going to see some basic how some basic principles of MEMS uh, are used in making simple sensors. Two sensors we will discuss in details. One is pressure sensor, other one is accelerometer. Okay, so before starting, any questions like specific thing you would like to cover, like ask, you want me to cover, you can ask. Otherwise, we'll just continue. Okay, so just try this. Yeah. So to start with, what is a pressure sensor, or specifically we can say what is a MEMS pressure sensor. Although there are pressure sensors that has traditionally been used, mechanical pressure sensors and this, but we are here talking about MEMS pressure sensor. Okay, so you see how small these pressure sensors are. MEMS pressure sensor, like if one pressure sensor is taken, like three pressure sensors can be pasted over the head of a simple pin. Okay, so such small devices can be used. So they what is the principle? They use a thin membrane formed on or in the silicon chip. So there is a thin membrane, like we have been discussing about bulk micromachining in previous class, how we etch out. And you see that if this is 100 plane, top and bottom will be same plane. So this will be 111 plane etched out. So it will have an angle of, yeah, anyone can say what is the angle here? Okay, I have already written. Yeah, 54.7 degrees angle. According to that, it will etch out and it will form a cavity. This since we are removing most of the silicon and creating a very thin membrane, it will be considered as a bulk micromachining. Okay, so sensing mechanism uh, detects the movement of the diaphragm. There can be different mechanism to detect those movements. There are okay, there are three ways in general we use to detect this. One is piezoelectric effect, where uh, changes in stress and strain uh, release like produce change in potential. Second is capacitive sensing. Third is piezoresistive sensing. We'll see how these works, how these are fabricated. Here we are mostly focused on fabrication of these devices. So when we talk about pressure sensors, we need to know some basics about pressure sensor. Like all the pressure sensors uh, does not measure the same thing. Pressures can be of three ways. They can be absolute, gauge, or differential. Absolute, in which there is no reference. Second is the most common one is differential. That is where there is a comparison, like one side, say we have fixed the pressure, say 1 atmospheric pressure, and other side, what is the pressure? Based on that differential pressure or relative pressure, we can say, relative to atmosphere. This is one of the most common ways of uh, doing the pressure calculation or measurement with respect to something. Okay, then gauge is something which we say that it is having some standards, like when we have this mercury barometer and these things, they are considered under gauge, like that with be based on some standards that is already defined. Some uh, like the mercury will be this high, like what will be the height of the mercury barometer when it is at sea level, at different levels, different pressures, that is defined. So these are gauge based measurement systems. So if we see these three types, okay, so how do they work? Piezoelectric, that means the, let's first talk about capacitive. We have been discussing about capacitive sensor in the second week also. So suppose that we have made a membrane um, like this, thin membrane over silicon substrate. Okay. Now above it, we create another cavity which can be hermetically sealed, like properly sealed. So some pressure is trapped here. Let's assume we are doing this at 1 atmospheric pressure. So while doing this bonding or sealing, we are doing it at 1 atmospheric pressure. That chamber pressure we are maintaining at 1 atmospheric pressure. So inside it, we have 1 atmospheric pressure already trapped. Okay. So, and here we have some conductive plate, and this, let me put some colors. So we have two conductive plates, one on the top and one on the surface of the silicon, the membrane we have created. Now, when we have same pressure out uh, at like inside this cavity, as well as when the pressure from this backside of this is 1 atmospheric pressure, there will be no change. The capacitance C, as we know, is equals to epsilon A upon D. And here, since we are considering that it is 1 atmospheric pressure air, okay. In some cases, like if we need to measure some higher, so if we need to measure some higher pressure, we can have some other fluid uh, at higher pressure sealed there. So that can be some other way, but let's assume it is air only here. So it is epsilon naught A upon D. So now area will remain fixed since we are not changing the structure. But due to the pressure, suppose from 1 atmospheric pressure, this pressure increases to 5 atmospheric pressure. Sorry. Yeah. So due to this, since this is a thin membrane, it will deform. It will be pressed towards the electrode and we will have a change in the shape. Due to this change, what we'll observe is that the distance d between these will change. D will change. It will decrease. Due to this decrease, what will change? Yes, anyone? What will change due to this?
Capacitance changes, sir.
When D is changing, what will change? Since capacitance depends on epsilon naught A and D. Epsilon naught is not changing. It was air, it is still air. Okay. But uh, further area is also not changing. But what is changing here is the D, the distance is changing. So if we put this in formula, if there is a decrease in distance D, we will see that suppose that let's make put it as C1. Now we put C2 equals to epsilon naught A upon D has decreased. So let's say it has decreased to 0.9 D equals to 1 upon 0.9 of C1. So we'll see that it will increase to say 1 point something C1. Okay, so it will be higher than the previous capacitance. This change in capacitance is what is measured, and as such we are able to calculate the changes. This has to be calibrated properly in like there are chambers which have standard atmospheric like standard pressures. We put those pressures and we will see the effect of those pressure over the sensors, and even to make it a bit stable, since the pressure will be like if you remember from Pascal's law, the pressure throughout it the fluid or air is the same. So to make it even more convenient, it is made like so that it is a bit stable and it does not break easily. It is covered, this whole membrane is covered and just a opening is left so that the pressure will enter through here and less disturbances. We will not see uh, non-uniform disturbances. If it is open, it can have different pressures over different part of the like different part of the sensor. So to make it uniform, more uniform, a simple tube like hole is kept. This is generally glass, so it is covered with glass with a hole or tubular like structure. Again, this etching is done just like we did bulk micro machining of this silicon. We can do similar to that for the glass. Second way is piezoelectric. Piezoelectric, in which on the top we will have some piezoelectric materials. Like when the membrane will change the structure. So in that case, instead of this, it is just reversed. That will have. I think I should use one new page. Just a minute. Yeah. So for piezoelectric one, this is the silicon. Let's put membrane here. Yeah, okay. Now we put some material which will respond to change in. I'm just putting theory. Exact implementation we will see when we will see the fabrication steps. Okay, we are putting some material that will have induced potential or change in potential due to stress or strain. And the advantage here will be it can very easily detect negative pressures also. Minus, sometimes we need some, mostly like in many industrial processes, we need to measure negative pressures also, like going towards vacuum and these things. That cases, like on the top. So when it will be pushed upward, due to this change in the shape, there will be stress. Okay, and this stress will lead to electricity or potential. And in the opposite case, if there is like negative pressure, when there is strain, again electricity or potential, but in opposite direction, negative. Okay, the value will depend on the amount of stress or strain generated, and that in turn is proportional to the pressure that is being applied, and as such we can have a calibration curve for this sensor. Okay, third way is piezoresistive effect. This is one of the most convenient way that is used, because here more than more than one structure in Wheatstone bridge calibration can be used. So, like remember, there were four resistances in Wheatstone bridge configuration, and then there was no current through it when it is fully balanced. Okay. Now, when we will have these four resistances replaced by piezo-resistive materials, that means when there is a change in stress or strain, very similar to this, the resistance will change. It is not compulsory to have this as a material property. Sometimes it can be due to structure also. Like suppose that we take a metal. Suppose that let's say copper we are putting, and we create a structure like this. Okay, copper structure like this. Now, when there will be stress or strain, the shape of this will change. We'll have contacts from here. The shape of this will change. It, or to make it even simpler, let's put let's take, we design a simple strip kind of structure on the top, and we are connecting it with electrodes. And this structure is over the membrane. So when there is high pressure from below, this membrane will bulge out, and as such, this structure will get stretched a bit. So this L will get increased by L plus delta L, and there will be change in the width also. Say W will become W minus delta W. Now, if we talk in terms of resistance, can anyone tell what is the formula of resistance in terms of resistivity? This R equals to, yeah,
O L by A.
rho L upon A. Yeah, very true. So now L is changing and A is changing. A here, since it is a seat, like it is not bulk like a wire. So we consider in such cases we are considering seat resistance only. So instead of A, we are replacing it with W for convenience, since the thickness will, let's say, remain the same. Okay, although the thickness can be, let's say we have put 500 nanometer deposition. Okay, so 500 nanometer. Uh, Although there can be change, there will be changes, but for simplicity, for calculations at present, let's assume that there is no appreciable change in the thickness. From 500, it might reduce to say 550, 450 maximum or something. Okay, so let's say instead of A, we are putting W. Now, if we check the change, that is here, R will, new R will now be rho L plus delta L by W minus delta W. Okay, so this change delta L and delta W, that change will determine how much pressure we are putting, how much change in the shape is due to the pressure. Now, why to go for resistive? Like if you see this structure, this is very similar to the capacitive sensor as well as piezoelectric. But if we see from the point of view of this calibration as well as instrumentation point of view, to measure resistance, it is much easier. Change in resistance, it is much easier. We can do it even using simple nowadays. These modules, Arduino modules, ESP32 modules are there. Using that, resistance change is very easy to model, as a resistance change will be modeled as a, yeah. Now, if you simply see, uh, if you remember a voltage divider circuit, so if we have a voltage, say I'm putting, let's start with a commercially available Arduino module or ESP32 that gives 3.3 volt. And if we just put our sensor here, um, let's represent it with such a structure. Okay, we have our sensor, pressure sensor. Okay, and we put a load resistance here, and we connect it to the ground of the board again. Okay, and we read this voltage Vx, or let's say I am putting 330 ohms. Okay, pressure sensor, let's say it has initial resistance, so R initial, we are saying it was 100 ohms. Okay, so can Can we calculate Vx? What will be the value of Vx? Yes, anyone? At least what is the formula that we will be using? Yes, anyone? Yeah, Venkat Lakshmi. Yeah, I think you are from electronics background, right? Venkat Lakshmi, are you there? Yeah, hello. Yes.
It will be 330, whatever 30 turns up. So, as per the voltage divider rule, Vx will be equal to 330 ohm divided by sum of the two multiplied by 3.3 volt.
330 by 330 plus 100 multiplied by V, or we can say 3.3 volt, right? So from the voltage divider rule, we can have this. Let's put 3.3 directly. So if we do some calculations, I think, uh, yeah, okay, I'll use this. So 330 divided by 430 multiplied by 3.3. So we'll get around 2.532 volt, right? Using ADC, like put it into ADC, we have 12-bit ADC in these modules. Like we don't have to make the ADC nowadays. It is generally available in these Arduino and ESP32 modules. So if you just connect it to the analog pin, you will be able to detect this when in initial condition. I am not talking about this whole Wheatstone bridge configuration. Let's talk about a very simple single resistance sensor. Now, if this resistance changes to say 120 ohms, now what will be the new Vx? Yes, any calculations? So load is still 330 plus 120 multiplied by 3.3 volt. Yes, anyone? So 330 plus 120 will be 330 upon 450, right? Into 3.3 volt. So we will get 2.42 volt. Now, based on this change, we can simply like the change is calculated for sensor point of view. The change we represent in sense of sensitivity, and when we are specifically talking about change in resistance, we will say it as delta R upon R initial multiplied by 100%. So what will be our sensitivity or response in this case will be like 20 ohms upon 100 ohms into 100% equals to 20%, right? Now, if we are talking in terms of voltage, if you see the change, so let's calculate just delta V upon V. So it will be 2.532 minus 2.42. That gives us 0.112 upon the initial voltage 2.532 equals to 0.044. Then we can convert into percent as 4.4%. So now we can have a map table like linear mapping of this, like 4.4% change in voltage corresponds to 20% response. Okay. Similarly, for different values, 20%, 30%, like, and then we will have a pre-calibrated curve from where we'll say that for 20% change in the resistance, what is the corresponding uh, pressure that we have. Okay. So based on such calculations, we can very easily implement a piezoresistive sensor compared to piezocapacitive, since measurement of capacitance in simple DC circuits is still a problem. We'll need a AC circuit, and in electronics, dealing with RLC circuits makes it much more difficult and complex compared to simple DC circuits where only resistance component is there. Third is this piezoelectricity, that actually the change, the produced voltage and the produced gradient is not always appreciable. Like, you will have to amplify it and then detect it. So this is one of the reason that piezoresistive MEMS sensors are one of the most commonly used. Okay, now we will see how these are fabricated. Yeah, any questions still here? Any doubts, any questions? Anything I missed?
No, sir.
Okay. So now let's talk about the fabrication of this MEMS sensors. Okay. So we start with silicon wafer preparation. That is, as we have discussed in last week, how we get a wafer, and when we have a wafer, we see that what type it is, and then there is first step, that is cleaning. So we will clean it. Generally, there are some standard cleaning processes like SC1 and SC2, standard cleaning 1 and standard cleaning 2. In if it is contaminated too much with organic contaminant, or by sometimes while sipping these wafers, when we have one or two wafers, they put a photoresist over it to protect the surface. In that case, you might need to use piranha or acid piranha cleaning for mild one, and not mild one, for some strong organic contaminant is there, or in simple cases we just go for acetone clean and IPA clean. We call it as degreasing. Okay, so this process can be used, and then we once we have the clean wafer, we start with first step, that is oxide deposition. So that again, like if we have a silicon, on top of it we need silicon oxide, SiO2. So as we know, silicon is a semiconductor, so that means it will have some conductive property. And as discussed in one of the previous class, that silicon as a intrinsic silicon is not available commercially, and it is easier to manufacture a p-doped or n-doped silicon. Starting in the manufacturing process itself, the doping is done. As such, certainly it will have some conductivity either due to hole or due to electron. Okay. So now if we want a non-conductive layer, although the processes are optimized for silicon, but suppose we don't want the conductivity from top to bottom, in that case, we generally grow silicon dioxide. There are two ways. One, you can deposit, but that is not of good quality. So thermal oxidation. Thermal oxidation generally, we grow silicon dioxide from silicon itself. Since silicon is there, we oxidize it. So oxidation will take place in a furnace of around 1100 degrees Celsius. It is done in a quartz tube. It will be put, and then oxidation will be done. So this will work as a masking layer for etching. So we have even discussed that for etching, uh, there can be different masking layers like SiO2 and silicon nitride. So it have two purposes. One is it can be used as an insulator. to put our this resistances over it, so that the resistance will this conductivity will not be through the silicon but through the uh, our piezo resistors only. Second purpose is to use it as masking layer to make these membranes. Third is lithography process. We have talked and we have seen a video about this, how we apply photoresist exposed to UV and develop to create a pattern. Then we will do the anisotropic etching using QH and TIMA that we discussed in the previous class. So we'll get a structure like this will be a structure, and we'll get it now like slanted side slanted side walls, not steep. Reason being, uh, we know that TIMA and KH, they etch out 1 1 0 0 and 1 1 0 planes, but 1 1 1 plane is not etched easily. That's why we'll see a slanted structure, and as such, we will make a membrane. Although it might look very simple when being talked like this, but it has to be monitored regularly. Like it will be dipped inside this steamer, and at regular intervals, you have to take it out, clean, dry, like remove all the contaminants, and then go to profilometer, which uh, which is used to measure the depth that has been created. Profilometer works very similar to AFM. We have talked about AFM tip earlier. It will have a tip, and that also is a MEMS tip that will move over the surface, and due to the change in this movement, we'll be able to check the depth that has been made. So it is done regularly, like after every 15-20 minutes, and it will be taken out, and then it will be checked and regularly after we have achieved the proper amount of etching, and we have the required thickness, because this the thickness of the membrane will determine how much flexibility it will have, as well as if it becomes too thin, it will get damaged easily and it will not be able to sustain higher pressure. Okay, so this is one of the things that we'll go for. Then this structure is made. Now the second thing is that in general, one step is missing. Silicon to etch silicon. Yeah, this is done. No, one more step is here. Polysilicon is deposited. Now there are two ways we can do. One is that to make the resistors on the top. Okay, top we have silicon dioxide that will remain as such. To make these resistors, we can use two things. One is some metal. Okay, but metal have the problem that when stressed out during stress and strain, they might break out. They might like they will chip out, as well as one problem is that some metal, in general, most of the metals try to penetrate below, like they will try to uh, diffuse through silicon dioxide and these things. There are like a lot of problems due to this. That is why you might be hearing that earlier processors used to have gold, then they shifted to aluminum, then like copper. They shifted to copper, then now they are trying to shift to aluminum. All these are due to the problems faced by different metals. So a better way is to use silicon here. But now silicon cannot be crystalline, since we don't have that easy way to deposit crystalline silicon over this. So using methods like we discussed, PVD, or CVD. Okay, we can go for deposition of polysilicon. Generally, CVD is used, that is better quality. And again, it will be patterned to make our registers. So it is like silicon on some color. On top of it, we have silicon dioxide. Okay, not that thick. Okay, then again we will have silicon layer over it. But this silicon is polysilicon. That is, polysilicon means polycrystalline. It is not having single crystal structure like the substrate. Okay, so on this polysilicon, now again we will do lithography. But before that, what is done is that, like, we cannot uh, dip, like dope it uh, at specific places, so the whole structure is doped. This is taken to chambers where this boron uh, boron doping is done. Boron precursor is there that will be used to dope it. There are some ways, like where, like, one boron wafer will be kept between two silicon wafers, like one, then another one for it, another one, like in sandwich kind of structure, and then boron will pass as we will put it in higher temperature. There are other processes, like very similar to chemical vapor deposition, where we use some precursors. Generally, when we are putting this phosphine gas for phosphorus, in that case, we will see phosphosilicate glass forming on the other side. These things are there. Okay, so this is doped. Why doped? Because we want to have a higher resistance, like higher conductivity. It should not be fully insulating. If it is simply silicon, we cannot guarantee the flow of electrons. Like we will not have like appreciable change in the resistance visible. That's why we make it a bit conductive, not conductive like metals, but we introduce some dopant to it. Now, once this doping is done, we will pattern it. How, how will we pattern it? We will have some resistances just on the membranes. Okay. Other things we will remove. Okay. So now we will have, if we see the top view, I will show the top view. That will be different. So we will have four resistances on the top, resistive structures, and now we have silicon resistances being formed there. Okay, then next step is metallization and bonding. Again, that will involve deposition and pattern. So if you see in this process itself, three times we have seen patterning, different processes, then patterning, and patterning in all these cases is being done using lithography. Okay, so if we see some, these are from some papers taken. Okay, so you see how they are adopting the process of making this different kind of pressure sensors. So here you see deposition, they are depositing polysilicon layer on. So first they are making SiO2, very similar to what we have discussed. Then on top of it, they are putting polysilicon. Then they are first removing, like patterning this polysilicon. So the step can vary according to what optimization has been done or what optimization they have planned. Okay, process flow can be different. Okay, so first they are making the resistances. Okay, instead of using this sandwich boron doping, they are using ion implantation, which is a bit costlier and sophisticated machine. So they might have this ion implantation available. So they are using ion implantation of boron. Then they are doing it again, like heavy ion implantation of boron. So they are making it like graded implantation. Over it, they are depositing silicon nitride to protect the whole structure. In our case, we didn't discuss like protecting the top, but that can also be done so that there is no cross conductivity. Okay. Then they are removing the silicon nitride layer from the top by RIE process, not removing the whole layer, but patterning it so that only the resistances are open now. Resistances or specific pads are open, and then other things are covered. Okay. On top, aluminum layer is okay. Aluminum layer is deposited. So these contacts they are using aluminum. Contact they are using is aluminum. So resistance is of silicon, polysilicon, boron doped silicon, and then contact is of aluminum. So uh, we will check uh, conductivity from these aluminum pads. So metallization is there, but this the actual sensing is done through polysilicon based resistances. Okay. Now, using this electrochemical etch stop process of the monocrystalline silicon using QH. After making all this, so what must be being done here is that they will be patterning the back of it using photoresist. So you see here some photoresist is pattern, and top they are covering with some rig. So in one of the classes I was telling about when we have to do some big process bulk micromachining, generally Teflon rigs are used. So back they will cover properly, and it is such sealed such in such a way physically that no TIMA should reach on the top surface. Just the back surface is to be held. So in this process, the silicon that we saw, the silicon wafer that we saw, generally when we procure have one side that is shiny, other side is not polished, not generally treated. It is a bit rough, okay, because most of the processes in semiconductor fabrication are done on the top surface micromachining. But in this case specifically, if we are going for pressure sensor, we have to get both side polished silicons, both side polished. Reason being, we have to process on both the sides. Lithography will not be perfect if we are not doing properly. As well as there is one thing that when you are doing the lithography on the back, it must be such aligned in such a way that it is falling exactly at the positions that we have defined the resistances earlier. To do this, do this like in lithography, there is a bit advancement that is needed for MEMS lithography is that there are cameras on the bottom of the wafer. They will take an image and they will align the top. So top and bottom both are aligned at the same time. It is not just that we have one layer, over it we are putting something, but we have a layer that is on the bottom of the wafer. So if it is a wafer, on the bottom we have these resistances. On the top, we will make patterns to create the membrane. So that is a bit tedious process, but due to the present technology, like we have camera capture as well as due to the software nowadays that is being used, we can have the complete image of the mask and we will like put over it, and auto alignment is even there. So if we have alignment markers over there on the bottom, there on the opposite side, it will be automatically aligned. And as such, these marks are done. Once this is done, it is sealed with glass wafer. Okay, and this sealing is done using anodic bonding. That is again a process where it will stick. So it will diffuse like uh, one single, one single structure. So complete structure. So this whole thing is closed. Now to have like based on our purpose or use, like they want that the pressure should enter from here and they will have a reference pressure on the top. So they are creating again using lithography these holes on the glass. But in some cases, like when I worked in on one of the pressure sensor, we went for having it hermetically sealed. So we while doing this anodic bonding, we went for having a fixed pressure. You can take one atmospheric pressure also as the reference, like that is what we do, but it can be changed. We can have a pressure of 2, 5, 10, or whatever we need. According to our need, we will have to put that pressure. Okay, inside we can put. In this case, it will not be a like the it will be able to measure the relative or differential pressure, but in this case the reference pressure is not fixed, that we will fix according to our need. But in case where you want to fix it, you will have to put that fixed pressure inside this cavity. Then there are like you see here again they are and from another work they are making the same thing but through a different process, through different design. But if you see on the top, you see here here they are putting different resistances R1, R2, R3, R4, and then R5 and R6 are there just for reference or calibration. They are not over the membrane. So if you see these dashed lines, there are four resistances, and in this case, instead of boron, phosphorus is used. Phosphorus doping is used. So the uh, conductivity will be different, as well as instead of boron, phosphorus is used. So they will get some like glass kind of surface forming on the back that actually helps uh, like that helps to do the anodic bonding when we are doing this glass and all. Okay, then you see how many metal layers are put. Aluminum, then on top again silicon nitride is used, then again it is covered, and at last we get a structure like this. Okay, again like I have taken some multiple sources, so anyway I'll be putting these slides. You can see that for the same thing there can be different processes, different way, the structure will look different. Concept is almost similar. Here also you see there are four resistances, small resistance, and if you zoom it out, you see that these are polysilicon ones, polysilicon resistor, and these are metal electrodes. And I think here they are using gold. Yeah, they are using gold as the electrode. There aluminum was used on the first, second, yeah, second also aluminum they are using. In this case, they are using gold electrodes. So based on your availability, your uh, yeah, in this case, there based on your availability as well as the facility, plus what kind of work application you are targeting. Sometimes, if it is say it is going to be used in space applications, where we need it to be working perfectly fine for say next 10-15 years without fail. So we'll go for, and there is no constraint on the cost. The constraint is just that the size should be very small, it should be lightweight, it should work fine. Then you can go for high-end processes that will yield better results, and like then you can produce even at a higher cost. But what if you are going to use it for like testing in water pumps, and if you just make the sensor so using so sophisticated all the top end processes, and at last we get a very good sensor, but that sensor cost is almost equal to the whole pump itself. So that is not what is preferred. So sometimes we have to think like what process we have to go for. Same process, like if you see this doping, okay, if we go by ion implantation, certainly it is much better, much controlled, but the cost also increases. Just to maintain that ion implanter, it needs a lot of cost. Its size is almost like a big hall, uh, like of 10, almost 20 by 20 feet or more than that, I can say. Such big instruments are there. So to maintain it, to have a cooling system, again the cost will increase. So these parameters we have to think when we are designing sensors. Same sensor, we can have different way of designing the same thing. Concept is important, how it is working. There are 2-3 factors that we have to take in mind when we are designing sensors, fabricating sensors. One is easy interfacing. Okay. Two is easy fabrication. It is not just that we are able to fabricate it very easily, but interfacing is very difficult. Like if we see this capacitive and piezoelectric sensor, the interfacing is complex compared to when we are going for piezoresistive sensor. So such things we have to keep in mind when we are designing sensors. Uh, it can be pressure sensor, gas sensor, humidity sensor, or accelerometer, whatever you are designing, that we have to keep in mind. Yeah, so any questions still here? Then we'll move to accelerometer.
Sir, at the bottom, we are keeping a hole and we are allowing the reference pressure, no, sir? At the bottom.
In this, the third way, they are not putting any hole. They are just putting a reference pressure inside this cavity.
Okay,
But
sir.
in this case, if you see, they are creating hole, and this hole, so they can maintain the pressure manually. Here, with the cavity, they can insert a pressure like they can put over a fixed pressure rig, you can say, and that pressure can be changed. So both ways are possible. One, you can have a fixed reference. So this sensor reference is fixed, you can say, like in this case, this last case, right? Here, you cannot change the reference point. But in this case, you have the flexibility of changing the reference point. But again, to make that reference, you will need some extra interfacing. You will need some specific design pressure, maybe using some pneumatic systems to maintain some specified pressure for reference that can be needed.
Sir, how to know the maximum power, maximum pressure that can be withstanded by the
That,
chamber?
yeah, that is actually done using while doing the calibration. Whenever you buy a sensor, any kind of sensor or any instrument, you see that there are some mentioned ranges. This is the
Yes,
minimum,
sir.
this is the maximum. It, that is defined using this calibration. So whenever we are making this, after that we go for calibration. We check it. What is the pressure it is changing? After that, after some point, it might not respond. Suppose that for some pressures it is going linearly. The change in resistance is going linear. Okay, pressure and then we say resistance is increasing or decreasing. Let's say current. Okay, is increasing linearly. After a pressure, it will just try to saturate. That change will not be significant because it is not a like infinite elastic surface, right? It will not change after a time, or it might break in some cases. So we don't go to the breaking point itself. We understand that after this it is not changing much. So we will define this as the highest limit from where the change has stopped. For very small pressures also, it will not change. It will remain same. So we define this as lower limit or LOD, limit of detection. This point where minimum is detected, LOD we define. Highest, you will generally see that there is saturation. We call it as saturation of the sensor. After that, it might not break at that point itself. It will saturate. The changes will not be able to uh, reflect their effect on the resistance or whatever mechanism you are using. That point we call as saturation of the sensor, saturation point of the sensor. And if you keep continuing even after that, it might break, it might like burst. So that point we generally don't go for. Our point of concern is between LOD and the saturation point. So we define our range based on this. Yeah, any other questions? Yes, anyone?
No, sir.
Thank you. So let's see some other sensors. Like one another sensor is accelerometer. Okay, this works on moving structures. This is very much a mechanical system. Like that you although that used a MEMS technique like bulk micromachining is not generally considered a part of semiconductor fabrication, but it is more uh, more related to MEMS fabrication. That is why it is a MEMS sensor, we can say, right? Here, although the structures are mechanical, we'll see that the structures are more mechanical, like they have moving objects and moving parts and all. But the whole process is being done over this top surface only. And here we will be using surface micro machine. So what is an accelerometer? These are very commonly used in our phones and these cars. Okay. So accelerometers measure acceleration forces using MEMS technology. Smartphone, automobile, even in aerospace is very commonly used. So the working principle is a proof mass on a spring deflection under acceleration. So a mass under hang by spring, when there will be acceleration, change in velocity. If it is going with a constant velocity, it will remain as such. When it will be accelerated or deaccelerated, there will be change. And this change or the deflection, this like, sorry, springs will be like this, right? Mass. Now, when by the Newton's first law, when there is no external force working, it will continue to remain at rest, we can say. So if this whole system is at a constant speed or constant velocity, not speed, constant velocity, maybe rest or velocity, zero velocity can also be there. It will remain as such, hanging. Okay. When we accelerate, the system is accelerating, then this will try to move leftward, and we will see a deflection in the leftward direction. This is just a principle. It is not exactly what we do. As I said that designing a spring in microsystems is not possible, like not easy, and that also a metallic spring, like almost an impossible task. Okay. And what if we are deaccelerating? It will deflect in this. So based on the amount of deflection, we can have uh, we can know what is the acceleration, amount of acceleration that is happening. Second, whether it is acceleration or deacceleration. Again, here it can be piezoresistive or capacitive sensing. Piezoresistive, in which there will be change in resistance, very similar to what we have seen in case of a pressure sensor. Capacitive, again, uh, parallel plate based. So the change will be based on, like I showed earlier also, comb-like structure when they will move up and down. So one comb is fixed, other comb is moving in between. So when it will move due to acceleration or deacceleration, this movement will change the distance. So let's mm, make an enlarged view. Say this is a fixed comb structure. It has this electrodes. Okay. So this we are saying as, say we are connected to plus some voltage. We have another comb structure in blue. We have another comb structure stuck in between, perfectly fitted in between. And when there is no acceleration, the capacitance is fixed, since here the distance d is same. Okay, d is same. Area of interaction is also same. Okay. Now when there is an acceleration, this is fixed. Sorry, this is moving. And this comb is fixed. Okay, so the fix will remain fixed, that is fixed to the surface. This moving part will move either forward or backward based on the direction and acceleration or deceleration. Okay, due to this change, there will be change in d, and this change in d will lead to change in the capacitance. And then measuring the change in capacitance, we can understand what is the change in like what is the amount of acceleration that is happening. So to start with, here we take a special type of silicon wafer that is prefabricated and a bit different from what we generally use, that is silicon on insulator wafers. This is a very new and growing field of semiconductor fabrication, in which we have silicon below, okay, then a layer of SiO2, then on top of it again silicon. And here, unlike the polysilicon I was talking about, this silicon is on the top and bottom, both are crystalline. How it is done? There are some 2-3 processes, but one of the common processes that I know is that they take a silicon wafer and then they grow SiO2 over it. So silicon and SiO2. So this is one wafer, and then another wafer also silicon, then back of it SiO2, and then they combine it, like they try to bond it using this anodic bonding and these processes. So this silicon comes from another wafer that is bonded over SiO2, and this thin layer is cut out. This thin layer, like whatever silicon we want, we keep that, and we remove the top SiO2, or we thin it out to get the desired thickness of SiO2. Just a minute. Hello.
Yes, sir. Yes, sir.
Yeah. Okay. So are you getting till here? What is being discussed?
Yes, sir. Just about the mass, again, you repeat, sir.
This
About the
mass,
proof mass.
this one, proof mass. So it is simply structure. You can say that. Let's uh, make it even simpler. That
Not here, sir. In the coating, in the construction itself, sir. In the fabrication itself.
fabrication, like there is actually there is no mass in fabrication.
At the top,
Mass is
SI layer is there, na, sir. At the top, SI layer is there, na?
mask you are saying, or mass you are saying. Mask, M-A-S-K,
Where I
mask.
thought that it may be acting as a mass. Is it not true, sir?
Which this one?
Last topic, sir. Recent slide.
Okay, this accelerometer
Next,
one.
next. This one,
Which
sir.
this one? This SI
The
layer
top
on
one.
the
The
top.
top one.
Yeah, that we are not talking about mass now. Okay,
Okay, sir.
that first we are talking about the wafer itself. The wafer here
Okay,
is
sir.
a bit different in the sense
Okay,
that
sir.
we generally start with silicon wafer, but in this case we have a silicon on insulator wafer. Okay, so this wafer is like silicon, on top of it SiO2, then silicon, and this silicon, the whole silicon is crystalline. In between there is a SiO2. This is nowadays being commonly used in case of FETs also, CMOS fabrication also. The advantage here is that if you see the FET structure, like source, drain, and gate, the whole conduction, everything is happening on the top. But these charges are coming from the bulk, uh, and that is why we need this bottom gate, sometimes not gate, sorry, bottom grounding we do in case of FET and all. Okay, so such structure, like when we have just top layer that is of our interest, and below it we put SiO2. The advantage we get is that the effect of traps here will not penetrate to the top layer. That is in terms of FET and CMOS fabrication. We are not going into that. So here, actually, this SiO2 is just a sacrificial layer. That is to keep these things in place till we want, and then later on remove this SiO2 at all. Removing this SiO2 will free this structure, and that is how the structure will be able to move. Okay, so first we take this as silicon over insulator layer wafer, then do the lithography for proof mass. That is, we define the proof mass, that is fixed structure, and the suspension structure using lithography. So on the top, on this silicon, we define what area we will make as fixed, what area we will make it moving. Okay. Then we go for deep reactive ion etching or RI, whatever is available. But in this case, since we need very steep structures, we cannot go for wet etching. No wet etching. Why? Because remember that the structures that we will be able to make using wet etching is slanted. And here we want the comb kind of structure to be high in aspect ratio. We want like very sharp features. So we go for deep reactive ion etching. As we have seen that plasma etching, deep reactive ion or dry etching, these give us better aspect ratio. Then release etching, that is we will remove. So we have Si, okay, again on top we have Si and this SiO2. Now what we did was we patterned it such that we just are keeping layer. Okay, so we have such patterns of silicon. Now that we are making this comb structures, we are making this one fixed, then this one is moving. Okay, again this we are making fixed, we want to make fixed, this moving. Okay, so to make this moving, what we will do is that we will remove the SiO2 from below it. Whatever fixed we wanted, we will keep it. For moving ones, we will remove. So we'll have this fixed structures over SiO2 and other layer, like they will be a bit floating in the air. Okay, and they are now free to move. So they are floating structures, although they will be hinged somewhere. Like if it is fully floating, it will fall out, right? So we keep it hinged, like at the last we just keep it like if it is a comb kind of structure. Okay, so we hinge it on these two sides. Okay, so like this, so it can move but to a limit only, it cannot go out. Then other structure, it is fully fixed and it is over a layer. So these are kind of floating structure, you can say floating structure. So when you move, it will move according to the acceleration, since it is free to float. There is nothing below it. It is in the air, as well as it is just hinged so that it is not coming out. Otherwise, it is free to flow. And after that, we do the
Sir,
metallization.
now
Yeah,
the movement direction is vertical and somewhere horizontally it is fixed, sir. Is it true,
this
sir?
no, this is not vertical. The
Displacement is vertical.
displacement is can be according to our use. It can be vertical or horizontal. Okay, it can
Okay.
be top down. It can be left.
But it
But
is fixed somewhere on the back side.
yeah, on the back side, like here you see on the two sides we are fixing it, and that fixing is not through a nail. It is again a silicon structure only. like it is one of the marvels of, you can say, uh, marvels of the present day technology, that we are able to make such structures. Okay, so the difference here, the basic difference here is that in case of pressure sensor, we used bulk micromachining and doping. Okay, removing bulk from the. In case of accelerometer, we use surface micromachining and deep reactive ionization. So that is the basic process difference. So here are some uh, structures that you see as MEMS sensors. Okay, some combinations like you see, it is hinged here. So this black box is the hinge. Okay, this black box is a hinge, and this whole structure, will be able to move around it. Whereas this structure is completely fixed, it will not move at all. And when it will move right, left, even like nowadays, combination of X, Y is there. Okay. In case we want Z direction, then we will need like going down and up. That will need like other complicated things, because then the measurement of change will be very difficult. So it is mostly like the movement that we are capturing is x, x, y, like moving up, down, like going forward, backward, or left and right. Okay, so accelerometers generally don't work when you like when someone jumps from uh, above to down. It until unless that phone or the structure is lying like that, the xy plane is on the in the plane of your jumping, it will not detect in general what we have. Okay, that's why, like if you see, if you keep your phone like this, the detection most the detection is best when you are moving forward and you have a gyroscope. We call it gyroscope, right? Gyroscope, that is again magnetic compass and all. Gyroscope with accelerometer in your phone, and if you are moving, holding your phone like this, it will give you the best it will give you the best acceleration and all. If you are holding it like this straight and then trying to move, it will be a bit difficult. Okay, just a minute. Don't know why okay. So if we talk about the circuit that goes in even after this accelerometer, the kind of structure is there, we need charge amplifiers, as I was telling about the problem with detection. Okay, so when we are talking about change in resistance, the circuit was very simple, a voltage divider circuit. But when we want change in capacitance, we need a carrier signal, charge amplifier, demodulator, low pass filter, instrumentation amplifier to amplify the change in capacitance, then different op-amp based circuits, and then finally we get the output. So the interfacing, when we have this, what do you say, capacitance change, the interfacing is complex compared to when we have resistance changes. Here the carrier needs to be AC signal or RF signal, okay, instead of a simple DC signal. In case of electronics, we have a lot of DC sources like battery, cell, different things. But AC, we need modulator, multivibrators to generate. That's why it makes it complex. So if you see some of the commercially available accelerometer modules that we use in case of that you can also use in case of you want to check the acceleration of a simple device. You can use this Arduino and ESP32s to measure this. You see here X, Y direction is defined and Z is crossed. That means Z detection is like Z detection is up down. So this one is able to detect in all three directions. So the way it can do is that either it can have it might be having accelerometers, like two set of accelerometer, one for XY direction, one for YZ direction, or three set of accelerometers, XY, YZ, and ZX. So all three planes it will detect, and as such you can get the complete acceleration in what directions you are intending. Okay, so we can say that some of the MEMS devices are just scaled down version of other big mechanical system. They use electrical or electromagnetic principles to control mechanical effects, commonly used in group rather than individually, like just making one device. That is not what is intended. Like there is a micro mirror array. Okay, so array of different small mirrors that is used. So it has reflector inbuilt, so field and like different kind of structure. So that is an electromagnetic mirror that is made. So there are different applications. I am just putting it like pico projector, where now it is, earlier you used to see that there used to be bulky projector, big projectors. Projectors were not that easy. Okay, that like not that handy. Okay, nowadays we see very small projectors. They are able to project from a very small lens, and that also a big screen can be projected. That is due to this micro mirror array. So inside it we have a lot of small mirrors that is able to like spread out the small image onto a bigger screen, instead of like earlier we used to have big lens projectors, and then the whole image was going out based on the diffraction of the light. Okay, how wide
Sir,
it can
what
go.
will be the cost, sir? Cost of this projector?
This I think almost nowadays we are getting it in 10-20,000, maximum even less than that. There are multiple. If you just search on Amazon or Flipkart, you
Okay,
will
sir.
find a lot of people. Nowadays, a lot of small projectors, like one very good projector, Sony. I think that was a bit costlier also, but it was 40-50,000, something like that. Okay,
Lifetime, sir? Lifetime?
lifetime it is.
Minimum guarantee, minimum guarantee.
Yeah, that I am not sure, but I think this will have a better life because it does not use that lamp kind of structure. Because if you see the previous projectors,
Yes, sir.
they
Yes, sir.
used to get uh, heated. A lot of
Yes,
heat
sir.
was needed and all. These are very handy nowadays. Even 4K projectors, they have come to this small size, all due to the micro mirror array that is a MEMS structure. So you see, we have a lot of technological advancement going around us just because of MEMS devices. So some of the applications of MEMS devices are accelerometer that we use in vehicle airbag, DLP projector, okay, cell phone microphones. So nowadays we see very good quality noise cancellation microphones. They again use instead of this magnet earlier big microphones, now they are MEMS microphones, this carbon microphone and all. Blood pressure monitor based on pressure sensor that we studied. These have come to market. They are again MEMS based. Digestible camera. small camera module that can be like instead of earlier you see there was one endoscopy, yeah, in which from the mouth a tube was inserted.
Yes, sir.
Yeah, that used to be very like not a very
Painful.
painful, yeah, not a very convenient way also, and that also people used to think it was inserted in someone else's mouth just before they stay, then they are coming. So it had stigma and all. Nowadays, digestible cameras are they're very small camera. You just eat it like a capsule. It will get into your stomach. Open it out. We can check images remotely. We understand the whole thing. Then it will come out fecal, through your fecus and all. Okay. Printer. The inkjet printers you see this cartridge. If you take it out, on the top there is the area from where ink comes. That print head is a MEMS, like that is made using MEMS. Image stabilization in nowadays the camera phones or they use a lot of image stabilization. That is again possible using the accelerometers we use in MEMS, from MEMS. Some other devices, if we see like Google Smart Contact Glucometer, that has come. If you search, like you just put with a this eye lens, it will be able to read what is your glucose. As such, your diabetes and this can be monitored much easily. Microchain drive, microchain and gears. Like you see, this is the gear and chain structure complete. Okay, so
Sir,
uh, yeah.
when we are calibrating, how
Hmm.
you are going to calibrate, sir? Whether you are using software or doing the experiment like a student and taking
Yeah,
the readings.
ev- whenever you have to make these physical structures, we have to do experiments, taking readings. Now, although like it has become much easier compared to when we were like working in our lab, kind of, we used to take notes. Nowadays, also we take notes, but there are better ways like you can just put it over Excel for simplicity, and then the linear calibration can be done, or there are specialized softwares in which you put the values, or sometimes from the calibration setup itself, like in the calibration setup we will connect the instrument, like which is measuring the resistance plus which is reading out the pressure that is being given. Based on that, that data is just accumulated, kept in the kept in the system, and based on that we can have graph and data sets, everything. So
Sir,
it's like,
is there any use of LabVIEW
yeah,
software for you?
lab view is used a lot, like not like I am more towards fabrication of sensors specifically. So we are not going for this like at present, since I am in PhD, I am not going for any commercial production.
Actually, general, I am asking
Yeah,
how much weightage of LabVIEW software is there
yeah,
in this field, sir?
it is like whenever we are going for automation, LabVIEW is one very easy to use tool. So certainly,
Acquisition is very good. No? Signal
yeah,
conditioning, everything is there.
signal control is there, and a lot of support is also there, in the sense a lot of devices can be supported. So it is mostly not dependent on the fabricated device that we are making, but our measuring instrument. Like suppose that we are measuring at present, when I am mostly working on gas sensors, right? So in gas sensor, we are accumulating data from this using IV measurement, okay, current measurement. So the SMU, source measurement unit, I am using, that is again compatible with LabVIEW. So we can easily, although it has its own proprietary software, but it can easily be, all the data can easily be collected using LabVIEW, as well as the input signals that we are controlling the gas molecule, how much gas will be input. That is controlled using MFC, mass flow controllers, and that is again interfaceable through LabVIEW. So certainly when we combine this system, we have created one system based on LabVIEW in which we can control the amount of gas as well as we can take the output from current, and a combination of this, a table kind of structure, a table kind of Excel CSV file can be output. So that is certainly there. We are also using LabVIEW, but not very frequently. We are using it as an application, you can say.
Sir, can we purchase any two MEM sensors and can we do a experiment with our lab facilities, sir,
That depends on your.
to check the characteristic?
Yes, yes, certainly you can. There are many facilities throughout, like you can write to some facilities which are testing, like Siri Pilani is one, CSIR Siri Pilani is there. Then in ISC, even here IIT Jodhpur, we are making a lot of sensors. So in case you need such things, or if you want to go for commercial ones, there are a lot of MEMS sensors nowadays. In IIT Jodhpur also, I know two, three groups are working over it. You can just like check the profiles of the different groups they are working over this, and you can have a like you can just drop mail, they might respond.
Okay, sir.
Okay. So what is the future of these MEMS? Okay. So they are sensing devices, low power. They can be used in medicine, robots, and drone. Cheaper devices, so mass production, and they can be integrated with IoT. We are seeing continuously improving quality and better MEMS technology, and uh, we are seeing a variety of MEMS application growing nowadays. Some of the application, like I said, this project advancement in projector, you might have seen in your lifetime only. And forget about lifetime, like we have seen it very recently. There's coming up of these cartridge printers that is starting of the this 21st century. So when we were kids, the printers used to be dot matrix and all. Now we have MEMS based cartridge printers, inkjet printers. So these technologies, we are seeing that the MEMS technology is expanding its horizon throughout the different fields and different applications. So we have some problems. Anyway, I'll just put this since we have very less time today. And you wanted that these crystal structures, right? So let's discuss some of it. Yeah. Any questions still here?
No, sir.
No. So should we start with this?
Yes, sir.
Okay. Yeah. So when we talk about silicon, like we said, it is having a structure similar to face-centered cubic. Face-centered cubic, if we say, uh, like on all the corners, we will have these atoms. Plus, on all the faces, we will have one atom. So if we just cut out a single, no, this single lattice, it will look like this, right? Corners. Now, uh, yeah, if we see all, there was one plane. I, okay, okay, not an issue. Now, if you see this, if you uh, see uh, 100 plane, which one will be the 100 plane? Yes, 1 0 0 plane. So x cutting the, if this is the x-axis, y-axis and z-axis. So cutting the x plane at 1, right? Then not cutting y and z plane. That means this surface is the 1 0 0 plane, right?
Yes, sir.
Right. Now, which one will be 1 1 0 plane? So x, y, okay, bottom, x, y, but not cutting the z plane. X, y we are taking here, not cutting the z plane. So this one is again 1 1 0 plane. But what about 1 1 1 plane? That will cut through this, a triangle kind of structure. Okay. Now this structure, if you see, if 1 0 0, so if you see from a point of view, like there will be one atom like this, one atom like from a lattice point of view. I am just showing one lattice. Okay, 1/4 of a atom, it will look like this, right? So the top surface, the atoms will look like this for a lattice. Same if you see for 1 1 0 plane. But when we see the 1 1 1 plane, it will look something like on one corner, like that is actually a bit complex to draw. If you just see this whole structure, if you make, and if you cut it with a plane combining this corner, not this one, this corner, okay, like this. If you cut it out, you will see that actually there are a lot more atoms visible, and that also very closely packed. Because if you see this atom, this corner atom, this corner atoms, like one part will be there. This top atoms, one layer will be visible. This bottom layer, like left corner, right corner, the central corner will be out. But this uh, front side face centered atom will be there, and back side face centered atom will be there. So there will be a very dense, like for the same area, you will see like a very dense kind of structure, dense kind of atomic structure. If you see here also, it will be there. One single atom will be visible, one face centered atom here, there, like that. If you see for one, see, if you compare this, okay, then uh, if you compare this with this 1 0 0 and 1 1 1 plane, there are a lot of atoms as well as very closely packed. There is a concept called planar packaging. In chemistry, you might have heard about, sorry, planar packaging, or uh, atoms per plane. Okay. Uh, I think actually I put the slide. I think that is still not synced here. Okay. Yeah, that is not synced. Two slides I put that. I will put that anyway here. Okay. After this, that in which we can calculate in a plane in one lattice area, like one lattice, how much, how many atoms are there. So seeing the number of atom itself, you can say that for that plane, the packaging is high. So we can say that if you check that 111 plane always have a like much higher density, not packaging, we can say, compared to 100 or 110 plane.
Yes, sir, understood. Yes, sir. Yes, sir, understood. The density is more, sir. Sir, understood, sir.
You can see through those slides also to understand what is the calculation. But frankly, like if we even don't go into calculation, if you just visualize a cut, like if you see this structure, right? This one is the 100 plane. Bottom one will also look the same, that 110 plane. But if you cut through the corner, this corner, this corner, and this corner, a lot more density is there. And that is one of the reason that 111 plane is very tough to etch. But at the same time, it has this advantage that if we are growing silicon, SiO2, silicon dioxide, if we are thermally growing, 111 yields the maximum, like it yields faster SiO2. Reason being, again, if it is 111, it has more number of silicon closely placed and densely placed. That is why more silicon is available and easy oxidation is possible. So it, in some case it is lagging behind, in some case it is faster. Okay, any other questions for here? Yes, anyone?
Sir, just checking, sir.
Okay.
Once, assignment, since I am checking, sir. Actually, in the, sir, you have said it is a diamond qubit structure, na, sir?
Yeah,
The
that
silicon
is
itself.
that is
Then
similar,
how many total silicon atoms will be there, sir?
same like FCC. It is
How
just
many, sir?
the orientation is a bit different, but it is like face-centered qubit, like six corners we have. Six, okay, sorry, eight corners. Eight, yeah, eight corners, and then on each of the six faces, one atom. Okay, so eight corners, one by eight, one by eight, so one, and this,
Sir, show the previous slide, sir. There is equation. Here.
yeah,
Okay,
yeah,
six
this one,
into
four,
six
four,
into 1/2, sir.
6 into 1/2. That is surface, like on the face. This one, face centered ones. Okay, and this eight will be 1/8. Because if you see, it is actually, if you see the letter, it is actually cut into eight parts. Each atom is being shared by eight unit cells. So we will have 1/8. Whereas this face ones, they are being shared with two, half in this and half in the other unit cell. That's why we have like 6 half half, so that means we have 3, and 8 1 by 8, that will give us 1. So in total, all 8 corners actually made up one atom in the unit cell because they are shared by 8.
Sir, generally, what will be the question, sir? Uh, will they ask
Questions
for a for
you
a cell, sir? Will they ask for a cell the number of atoms?
know, like questions in the
Just I am
exam,
checking. Just I
exam
am
you are
checking,
saying?
sir.
Yeah.
Somewhere I have seen, sir.
Okay.
Just checking. Somewhere he has shown on few objective questions there. It came, sir.
Number
But
that
I
actually
forgot
is
whether it is
6.
for unit cell or I
That
don't know. Just
for unit
forgot
cell
that.
only, because this number of atoms we can certainly
Per,
define for per
per,
unit cell only, because
okay.
when we go above it, then we will have to say like 2 unit cell, 3 unit cell, or the whole crystal we can't measure until unless we know how many unit cells are there. The question
Sir,
must be for unit cell only.
sir, in
Huh.
assignment 3, I got wrong in the problem, sir. I
Mhm.
have seen in the material itself a formula. Of, can I read the question, sir? Can I
Yes, yes,
read the question?
yes, yes. So,
Sir, what resolution could be achieved theoretically by E-beam lithography while applying a 25 kilovolts input, sir?
25 kilowatt.
That I took some
Kilovolt
formula.
or kilo electron volt it will be, no?
25 kilovolts is given, sir.
Okay, okay.
Kilovolts is given.
Kilovolts. Okay, huh.
But I got an answer where lambda is equal to some 49.2628 picometers. But that answer is wrong, and here the range is given 2 comma 5. How they got this answer? I need, sir.
No, what
Already,
formula you are using? Lambda equals to how much you are using?
HC, I think HC by E is the mass of the
Okay, no, you don't need
electron
to
divide by the
resolution.
input voltage, sir. Divide by the voltage,
Resolution
sir.
is not equal to wavelength. That you have found out the wavelength, right?
No, sir. Hc by ma.
Hmm.
That is the I think mass of the electron denominator. I am telling Hc divided by
Mhm.
Hc divided by.
No, but the
That is there
question,
in the material itself, sir.
okay,
Huh?
but the question is about resolution of
Yes, sir.
the
Yes, sir.
so once you have found the wavelength,
Mm.
okay, that equation is for finding the wavelength. But after that, you have to get the resolution of the E-beam lithography, right?
Then there is a statement, sir, in the
Huh,
material
huh.
that D should be the gap that should be greater than
Gap.
lambda
So
by 2. That is
greater
the condition
greater
given.
than, not lambda.
Lambda by 2. 2.
Rayleigh criteria is not lambda by 2, na? 2 lambda is there, na?
In the material, it is given, sir, lambda by 2.
It
In
is
the
based on,
material, in the
okay.
lecture
So
material,
yeah, so what you do is that if there is such confusion, you just drop maybe like sometimes sir might be saying something, and this is just a generated, what you say,
then
subtitles, right?
then I got a doubt whether I have to put the lambda value or lambda by 12. But the answer is between 2 and 5, very much far away from my answer, sir.
No,
Actually,
because
the range is
actually
given 2 comma 5, sir. The range is given 2 comma 5,
5,
which is not needed to my values, no, sir.
2,5
I gave the 49
picometer, or what unit?
picometers, picometers.
Picometer. You
Mhm.
see, like what we generally do is that if we talk in terms of different kind of lithographies, the resolution depends on lambda for sure, okay, but there are other factors also, and it is mostly defined using not directly by wavelength, from Rayleigh criteria, If you see now, Rayleigh criteria is there. If you go by that, then there is a derivation, and then resolution of this e-beam lithography is something like 2 square root of this lambda and all. So I exactly don't remember the formula. It is a bit different than lambda.
I
That
posted
answer
the question in the forum,
forum,
sir,
yeah.
by asking the solutions for
Uh,
the problems, sir.
Solutions will be uploaded. Uh, what I see that in the previous years also, previous semester and all, the solutions were given. Okay, so it must be uploaded soon. Okay, actually, like I am not dealing with that part, and we don't know what is going on in
No
that.
problem, sir.
Yeah.
Generally,
Uh,
you will be giving an idea about the formula, sir, like that
mhm.
one. Sir, is there any next class, sir? Any
No,
in one more?
this these are like four only. In case I get a mail for some extra session, then I like that you will get a mail. But till now, that is all.
Oh,
That's all.
okay, sir.
Yeah.
Thank you very much, sir, for your interesting discussion with us. Thank you, sir.